SQL, Structured Query Language. This is the most important, most useful computer language to know. Yeah, okay, those are fighting words. I've just annoyed a whole bunch of people on the internet who'll be complaining, how can you say SQL is the most important? What about Python? Or what about Java? Or what about C++? Or Swift? Or C Sharp? Or Kotlin? Or Rust? And okay, those languages are all great, but SQL is different. It's kind of in a class of its own. So let me begin with a few reasons why I say this is the most important, most useful language. First, SQL is universal. It is ubiquitous. This is a language used across every platform and in every kind of software. Web development, mobile development, desktop applications, and it's proven. You're going to find SQL in these legacy mainframe systems that have been running for 3 or 4 decades. And you'll also find it in the latest, most recent cloud and AI software, because SQL is a fundamental skill for doing any kind of software development or data science or data analysis. But unlike many of the other languages I just mentioned, SQL is still incredibly useful, even if you're not a software developer or data scientist, because you can just use this language in many existing desktop and web applications like Tableau or Power BI or Google Sheets, because it's just part of the landscape of business now. And SQL is also one of the simpler and smaller computer languages you can learn. This isn't like learning a foreign language where you need to build some massive vocabulary of hundreds or thousands of words before you can say anything useful. No, here, as you're going to see, you'll be able to do almost everything you'll ever need to do with this language with maybe 20 to 25 words of SQL. But you do need to really understand the impact of using these words, the ideas they represent, and how to put them together successfully. Now, before we go any further, let's get very clear on the point of this language. SQL, and some people say SQL, I'll talk about why. This is a language you use to work with databases. That's what it does. That's all it does. If you don't have a database and you don't want a database, there is not much point in learning SQL. But let's face it, most organizations already have multiple existing databases. So when you need to be able to get to the data in one of those databases, you need a way to reach in and pull out just the parts you're interested in and ignore the rest, to find some information when you're not sure where it is. If you want to group some of this data together and sort it and summarize it, or combine this data over here with that data over there, to ask questions of the data, to interrogate it and get the answers and the insights that you need. And that's what we're going to do here. Now, a lot of this will be about retrieving information from an existing database, but you'll also see how to use SQL to manipulate the data, to add new data or change it or delete it. And in this course, we'll mainly focus on how to write SQL to work with an existing database. It's true SQL can also be used to create a brand new database and then administer it and manage users and manage permissions. I'll talk a little bit about that aspect, but database administration is not the focus here. And if you're wondering why, it's simply because most people don't need to do that. And as this is an introduction, I'm going to concentrate on what most people need to do with SQL most of the time. Now, okay, I expect some of you have already written or experimented with SQL. Perhaps you picked up a little bit of it here and there, or you copied and pasted some SQL somebody else wrote and then edited it a little bit. But if you've never felt comfortable with this, if you wonder if you've been doing things the right way or the best way, then welcome. And yes, you're in the right place. But to be clear, you don't have to know any SQL right now. And even if you do, I'm going to ask you to just set it aside and just reset for a few minutes. Let's begin at the beginning. Begin as if you've heard these 3 letters SQL, you've been told this is important, but that's all you know. Let's start there, because that gives us the best way to talk about what this language is, what it's intended to do, and what you need to think about before you actually start writing it. I'm Simon Allardyce. I've been writing SQL for nearly 40 years and teaching it for over 20. And my goal for this course is to be the single best introduction to SQL you can find. Those are also fighting words. So let me prove it, and let's begin. Okay, I get it. You're impatient to start writing SQL. You're thinking, okay, I'm ready, let's go. Just tell me what to type and where to type it. But I'm going to ask you to hold off for just a few minutes. Now, there are some other languages where I might begin that way, where we could just jump right in. I would tell you to type a simple line of code, and then I'd explain what that code does. Like, here's some basic Python to add two numbers together, or here's some Swift that displays a sentence on the screen. But that approach doesn't work here. It doesn't work with SQL because even the simplest SQL you could ever write always assumes a bunch of background knowledge about databases. Let me give you an equivalent situation that has nothing to do with computers. If you've heard recordings of air traffic controllers.
Shamrock 472, VFR approach, runway 27 left, report middle marker.
Air traffic control, or ATC communication, is in English, but it's a very specific usage. It's certain words in a certain order. And it's the same with SQL. We use English words like select, update, order, group. And where you have to say, or okay, write these words in a specific sequence or it won't work. And if you're thinking, yeah, just tell me what to write. Well, if I do that, it's kind of like saying, all you need to do to become an air traffic controller is recite the line,
cleared for ILS runway 24 left, hold short of Delta.
Now, sure, you could just repeat that sentence. But if you don't know what that sentence is actually talking about, it's not going to work out very well. Because for any communication in air traffic control to make sense, you first have to be comfortable with aviation concepts like aircraft call signs, airspace rules, landing sequences. And here, for SQL to make sense, you first need to be comfortable with database concepts and terms like tables, rows, columns, indexes, data types, but also primary keys and foreign keys, relationships, even referential integrity. You don't have to become an expert on all of this, but you do need to understand what it means. I was once asked, can we just set aside all the database stuff for a minute and just focus on the SQL language? And no, that's kind of like saying, can we learn ATC communication but not talk about airplanes or runways or airports or flights? And you can't. Everything you say in ATC communication is about those ideas, and everything you say in SQL is about databases. And that's why I need to take just a few minutes to cover the most important ideas, the core concepts, the database terms we have to understand. So when you write that first line of SQL or your 500th line, it actually makes some kind of sense. Now, if you feel like you already know all this stuff, if you're thinking, oh, I've been using databases for years, I know about tables and rows and columns, well, that's great. Consider some of the other terms I mentioned, like primary keys and foreign keys, relationships and referential integrity. If you're good with all of that, you are welcome to skip ahead. Or you can just sit back and sing along for a few minutes. This won't take long. But let's get clear on the fundamental database terms and concepts, because it's what every line of SQL needs us to understand. Sidebar. When you see these three letters, you will sometimes hear it pronounced as SQL and sometimes as the word SQL. For example, if you're talking to people at Microsoft, they usually say it as the word, not the abbreviation.
SQL Server.
Aftermath of SQL.
We're going to create a SQL database.
But if you are at a conference for the open source database platform, you will more often hear the abbreviation.
MySQL database service.
The whole ordering system and such runs on MySQL.
So there's often a common style within one particular technical community. But even then, I know people who say Microsoft SQL Server instead of Microsoft SQL Server. I know people who call this product MySQL, not MySQL. It's like other technical terms like GIF versus GIF or router and router. Okay, some people will try and tell you there's only one way to say it, but in practice, you're going to hear both ways. It doesn't matter very much. However, there is one common misconception about this. It's easy to think that pronouncing this as SQL must be just somebody's cute way to take the letters SQL and trying to turn it into a word. It's kind of the other way around. You see, back in the 1970s, when this language was being developed, they called it SQL, spelled out in full as a word. It was an acronym for Structured English Query Language. And then they realized another company already owned the trademark SQL, so they had to pick another name. But this language was called SQL before it was renamed to SQL. So both ways of saying it have been there since the very beginning. Now, what do I say? I usually say SQL if I'm talking about the language by itself, but I'll say SQL when I'm talking about specific products that are usually pronounced that way, like Microsoft SQL Server. And sidebar, let's move on.
Data store.
Or
a database is a repository of data that is defined.
these kinds of definitions are true but useless, because you could just as easily use this to describe a folder on your desktop where you've gathered a few related documents. Look, I now have a collection of information. Or I could copy a bunch of PDFs to a memory card and say, look, I now have a repository of data. So is this a database? Well, in the very loosest sense of the word, maybe, kind of. It's not what we're talking about here. We want to work with database software, this entire category of products and technologies, including Microsoft SQL Server, Oracle Database, IBM's DB2, MySQL, PostgreSQL, and many, many others. Now, we all deal with databases every single day, whether we're consciously aware of it or not. Most of the time, the database stays behind the scenes. We don't directly log on to a database. Instead, we visit a website and the website is using a database. Or we use a mobile app and it's using a database. But whether it's a business application, your HR systems, sales and inventory, customer relationship management, or when you shop online or use social media or check in for a flight, we are continually interacting with databases every day. But still, there's a common misunderstanding about why databases even exist and what problem they solve. Here's what I mean. Let's say I'm talking to a room full of business professionals, and I just ask the room a simple question. What is a database for? Now they'll think about it, but the most common response I'll get is something like,
well, a database is like a place you store important information.
I totally understand why people say that. It's not a great answer. And thinking of a database as mainly just this kind of storage location kind of misses the point, because we don't need a database for just that. If I had some information about a new customer, well, I could just write it in a text file or put it in a spreadsheet and save it to my desktop. But if I'm trying to run a business or a team or a project using this data, well, this doesn't scale. I might be able to keep track of 100 customers. I certainly wouldn't want 200,000 or 1,000,000. And this isn't shareable or available, whether that's shared across my team or made available across the world. So all the latest information, the most recent changes are always visible on a public website. It's not secure, protected from hardware failures or internal issues, but also making sure it's backed up and it's easily recoverable. And also there's nothing to prevent this data from being deleted or changed or corrupted. There is no data integrity to ensure this is accurate or trustable in any way. Nothing to stop me just opening this document and typing it full of garbage or duplicating it a dozen times where nobody knows which version is the right one. And these are just a few of the problems that databases actually help with. It's not about just having a place to put our data. It's about having an organized system you put your data into. And when you put your data into that system, it will help us with all these other problems. Now, this is why we use database software, or what's typically called a database management system, or DBMS. Microsoft SQL Server, Oracle Database, MySQL, etc., etc. They are all database management systems. And we use a DBMS to then create and manage and work with one or more databases. And the DBMS is the software that continually runs in the background to keep those databases up and running, control access to them, and make sure all the various rules are applied. And even though there are many different database management systems from many different competing organizations, most of them support using SQL as a language to talk to the database. But in order to write SQL, we have to understand at least a little about how that database was defined, what's the structure of it, and what are the rules that exist inside it. Of popular database management systems will include names like Microsoft SQL Server, MySQL, PostgreSQL, Oracle Database, IBM DB2, SQLite, MongoDB, Redis, Microsoft Access. All right, many of these have been available for a long, long time. That Oracle database software was first released in 1979. Microsoft SQL Server came out in the 1980s, as did IBM's DB2 and PostgreSQL. Now, if you're wondering, am I supposed to know all these products or memorize all of them? No. The thing is, SQL applies to all, well, nearly all of the technologies I've just mentioned, and many other products and applications too. As you can see, the term SQL is actually in the name of many of these. But even though there are a lot of different database management systems, they can be grouped into a few broad categories, and the most common are what are called relational database management systems, sometimes abbreviated to RDBMS. What that means is they were all based on the same concepts, they use the same terms, they share the same ideas about what a database is. These ideas were from a fellow called Edgar Codd, who published a paper on the relational model of data back in 1970. He came up with this general approach for how to structure and organize your data, and it's been incredibly influential, very effective, very successful, which is why these products have lasted for so very long, because they work and they fix a lot of classic business problems. And SQL, the language, was also designed around exactly these same relational database ideas. That's why we can use SQL with so many of these different products. Okay, there are a few database management systems that don't use SQL. For example, Redis and MongoDB, these are two popular database products that intentionally took a different approach for managing data than that typical relational database approach. And you may even see products like these described as no SQL or no SQL database systems, because one of the things that's most notable about them is they don't use SQL. But this is an SQL course, so we're going to set those ones aside. We're going to focus on the majority of database products that do use SQL and use these relational database ideas and what that means. A few organizations try to have one database to rule them all, a single corporate database that contains every piece of company-wide data. But in practice, it is much more common that you'll find multiple databases in one organization. And those databases can exist for very different reasons. Sometimes the database is created to support a single business unit or a single department, like having a human resources database or a finance database. But other times it's organized more around a business task, like purchasing or customer relationship management, and it spans multiple departments. Now, some databases exist to support real-time day-to-day operations. They're kind of a working document of the transactions happening right now. Other databases might exist to be more of a historical record and an archive of what has happened in the past. Or you might have one database that exists to just hold the content for your public-facing website, with maybe a separate database that holds the website analytics and usage information. And in many organizations, you don't just find multiple databases, but multiple database management systems, like having SQL Server and Oracle, or DB2 and MySQL, or PostgreSQL and Azure SQL. Some of those databases might be on premises, meaning they're running on computers at that location, but where others are running in the cloud. Because it's more and more common to find multiple solutions. It's another reason why I'm going to take a vendor agnostic approach here. I'm not going to be showing you SQL just being used in one DBMS or one application, but how this can apply to any of these. Every database has a fundamental reason to exist. What's it for? What does this store data about? Is it people or products, transactions, perhaps documents or media or website analytics, or even all of the above? And when a database is being planned and designed, part of the process is to identify all these different pieces, the different elements, all the different things that it needs to store data about. And in the early stages of database design, what's often called data modeling, the term entity is often used because it sounds a little better than saying thing or stuff. What are the different entities that will belong in this new database? For example, if the reason for a new database is to support some kind of e-commerce operation, then the important entities, the things we would naturally talk about and expect to store data for, would include ideas like a customer, a product, an order, an invoice, a payment. But if instead we were making a database to support, say, classroom logistics for a corporate training center, then we might begin with entities like instructor, student, classroom, course, event. And in our new database, we would create a table for each entity. And a table is the fundamental building block of every relational database. We must have at least one table. We will typically have multiple tables, sometimes dozens, sometimes even hundreds of tables in one database. And without tables, a relational database is useless because there's nowhere for your data to go. All of our interactions, saving data, reading it, updating it, deleting it, we don't do them with the database as a whole. They are done with a specific table inside the database. Now, to be clear, that doesn't mean you make a new table for every single customer. No, it means you would have one table that holds customer data, another table that holds order data, and another table for all the product data, and so on, where each table consists of very well-defined, structured, and repeating data. And here's where we run into quite a common misunderstanding. Because if you've ever used or even just watched somebody else use a database, whether it's a simple desktop database like Microsoft Access, or any application that actually allows you to see the data in a table, you're usually going to see a grid view of rows and columns of data. And a lot of people's first reaction is, oh, that's it. So a database is kind of like a spreadsheet, just more expensive and more complicated. And okay, it might look a little bit like a spreadsheet, but first, you're only looking at one table here, and there might be dozens or hundreds of tables in the same database. But more importantly, what you don't see is everything the DBMS is doing in the background. It's enforcing security on that table to make sure we have the right permissions, whether we're allowed to add new data or edit any of the data, or possibly not even look at it at all. And if I had data or changed anything, it's going to make sure that that data is meaningful, where I can only add the right kind of information. But yes, a table in a relational database can be viewed as rows and columns of data, but it's much more controlled and constrained than a spreadsheet, and much more powerful than a spreadsheet. And if we're going to be writing SQL to get to that data, whether it's to read it or change it or add new data or delete it, we need to dig a little deeper into those tables. With any table in a relational database, we can think of the data as this grid of rows and columns. Columns, like columns in architecture, run vertically. Rows run horizontally. And each row in a table represents a single individual item of whatever entity this table represents. For example, if we have a customer table that holds all of our customer data, then each row in this table is one specific customer, whether there's 5 rows in that table or 5 million. If we have an order table, each row is one order. If we have a patient table, each row is one patient. And then the columns describe each distinct piece of information we want to keep track of for that entity, like a customer email and a customer phone number, a customer postal code. Now, some tables might only have 2 or 3 columns. Some tables might need 50 or 60. And when you're defining a database, you first figure out what tables need to exist, and then you define what columns are needed in each of those tables. Because we cannot add any new data to a table until we've said what the columns are. That's because within each table, every row is going to have the same structure. It's going to have the same arrangement of columns. So one way this is different from the idea of a spreadsheet is that tables in a relational database are intentionally not flexible. They're not free form. When you add a new table to a database, you don't just get the equivalent of a blank spreadsheet. You can just start typing random data into. No, we need to decide how many columns each table needs. We have to give each column a name, and we also have to say exactly what type of information, what data type is allowed to be in that column. So if we're defining an employee table for a human resources database, we might want columns to represent each employee's first name and their last name and their email address and the date they were hired and if they have a bonus percentage and are they currently full-time or not and so on. But we would also say, well, these columns have to be text. This must be a date. The bonus percentage has to be a number, and this column should only allow either true or false. So from the very beginning, every database starts to have rules and constraints to make sure the data is always meaningful. And the database management system, the DBMS software itself, is going to enforce those choices. If that column is defined as a date, and later I try and write some SQL to try and insert a different type of value, like a name or an email address or an image of a cat, even if my SQL is written correctly, the database will refuse it. It will not allow data that doesn't conform. Every column must be defined, and the database itself will keep it aligned to that definition. Every column in a table has a name, and it also has a data type. What kind of values are allowed in that column? Now, even if you're not involved in making that initial decision, it is still important to us when writing SQL. Because if we're trying to read information from a database, or insert data, or change data, we need to know what type of data to expect from that column, or what kind of data we're allowed to put in it. Now, if you have any background in programming, you already deal with data types, and it's a similar idea here. Broadly speaking, we need to understand first, does that column hold some kind of string value, meaning it's text or character data, or is it some kind of numeric value? Or perhaps it's a date and or time. Some columns might be just this simple Boolean value, meaning it's either true or false and nothing else. And sometimes a column could hold a binary attachment, like an image file or a document. But even within each of these, there are often multiple options, because the DBMS wants us to be very specific about the data types so it can be efficient about how to store that data. So with text data types, some columns might be a fixed length, like having just a 2-character state abbreviation, but others are going to need to be variable length. But even then, you can often say, if you expect that column to have a small amount of text, like a first name, or a large amount of text, like the contents of a blog post or a legal contract. If you're storing a number, sometimes you just need an integer, a whole number. Other times you need to support the decimal point for financial transactions or scientific data. And when storing binary data like an image file or a document, there's usually a binary data type, but there's often also a distinction between small files and large files, which are often referred to as binary large objects or blobs. Now, okay, I'm not going to try and cover every single option here, and we don't need to. Just enough to realize that when you're dealing with a database, you often think, okay, I'm going to get some data from that table, so I need to know what columns exist and what data types they are. You may see something like this. Here's the definition of a simple product table. Now, we're not seeing any actual data here. It's just each column's name and each column's data type. So we begin with the product ID column. This is defined as an integer, a whole number. Then the name column has a data type of varchar 100, meaning a variable length character data. We don't know exactly how long each product name is going to be, but it shouldn't exceed a certain size, in this case, a maximum of 100 characters. Next is the category. This is also defined as varchar here, but this time it's a shorter length, a maximum of 50. And then we have description. Now this is defined as a text data type. So this is also character data, textual data, but this doesn't have a maximum size. I can store much larger amounts of text in this description column. Now, okay, some of you might be thinking, Well, hang on. If this text data type is much more flexible and we could store anything in, why don't we just use this for any kind of text rather than this varchar version? And it's a good question, dear viewer. The reason is that when we define a column that has a fixed length, or at least a maximum length, then the database is able to be much more efficient about how to store that piece of data. But if we're using a more open-ended data type like text, where any value in this column could be 10 characters, it could be 25,000, who knows, then the database has to store this in a different way, and it's not as efficient. And what that means is later, if I need to do any kind of operation using the values in these columns, like writing SQL that will search them or sort them, it will be much quicker doing it on the column defined as varchar than it is on a column defined as text. Moving on. Stock quantity, this is defined as another integer, just a whole number. And then price is a different kind of number, defined here as the data type decimal. It allows us to have up to 10 digits before the decimal point and 2 after. Then we have date added is a date, and finally is active is a Boolean. We will only allow either true or false values here. Now again, I'm not trying to explain every single data type, and you will find that the exact options do vary a little bit between different DBMS systems, but the core ideas stay the same. One very important question: when a new row is being added to any table, is a value required for every single column, or is it ever optional? Now, the default state of most databases is that all columns must contain values, but sometimes that doesn't make sense. For example, we might have an employee table with columns for first name, middle initial, and last name, but we could recognize some people don't have a middle initial. Or we might be storing address information for a customer. We might require them to have an address line 1, but not require an address line 2. So these columns can be defined to allow null. And null is a very important idea in relational databases. It is not the same as just a space or a zero or an empty string. Null means the complete absence of a value. Making the decision about whether a column does or does not allow null values, that's up to the database designer or database administrator. But if we're going to write SQL, we often need to know, are there any columns here in this table that allow null? Do we need to think about that? Because if we're retrieving data from that table, we need to understand we might get these null or non-existent values. Perhaps I might even only want to bring back those rows where that column is null, or where that column is not null. So we often need to engage with this idea and the word null in our SQL. Whether we have a customer table with 1,000,000 customer rows, or a patient table with 100,000 patients, or even a user table with just 5 users, we always need the ability to go directly to one specific row to get the data for this particular customer, or update that particular patient, or delete only that user. Now, the typical way is that every table will have one column that's designated as the primary key. Now, for a column to be a primary key, it has to contain unique values. So even if there are 1,000,000 rows in that table, no two rows are allowed to have the same value in that column. Now, they might have identical values in other columns. Now, if we have a lot of employees, some are going to have the same last name. Some will have the same birth date. Some will have the same state, the same city, but they cannot have the same primary key, because the primary key has to take us to one and only one row. So we cannot allow duplicates. Now, sometimes a piece of data that we've already decided to store is good enough to be the primary key. We might decide that for our user table, the email address should always be unique. So we could use that as the primary key. Or if we had a table that stored vehicle data, we might say that the existing VIN number should uniquely identify each row. But often there isn't a single piece of data we can guarantee to be unique. So for many tables, we'll define a new column just to act as the primary key, often an ID column of some kind, like a customer ID or order ID or a patient number. And we can also tell the DBMS to automatically generate a unique value for that primary key for every new row that is added to the table. Oh, so you're adding a new customer? Well, the last one was customer ID 1148, so this one will be customer ID 1149. So the database itself can take care of incrementing that number automatically for each new row rather than us needing to manually figure it out. And the primary key is such an important idea that whenever you're looking at the details of the table, even if it's just a list of columns or some kind of application that allows you to see a graphical representation of a table, you'll often see the words primary key on one of the columns, sometimes abbreviated to PK, sometimes as a little icon of a key, but it should always be very apparent which column it is. One of the huge benefits of having these unique primary keys that can identify a single row in a table is we can use that information in other tables as a reference. For example, let's say we have a customer with the unique customer ID 1148. And now, when we're creating a new order, rather than copying and duplicating a bunch of data about this customer, we just define a column in the order table with customer ID. And this can act as a reference from the order table back over to the customer table. Now, customer ID is the primary key in the customer table, so it's unique. There is only one customer row with this number. But in the order table, this does not have to be unique. We could have several orders with the same customer ID 1148 because the same customer could create multiple orders. And what we're describing here is a one-to-many relationship, very common in relational databases. One customer can have many orders, but each order is always for just one particular customer. So here in the order table, what makes each row unique is the order ID. That's the primary key here. So in this table, the customer ID column is still a key, it's just not the primary key. Instead, it's called a foreign key. It is a key to a different table. And we tell the DBMS that this column is a foreign key, so it's going to check the validity of whatever data we put here. What that means is that the database won't let us create a new order row for customer 1148. If there is no customer 1148, it will check to make sure that this information is valid. The database will also stop us from deleting a customer in the customer table if there are still existing orders that refer to that customer. And the term we use for this is referential integrity, sometimes called relational integrity. But it's back to this idea that the data will be kept consistent within itself, always meaningful, even when multiple different tables are involved. As you work with different databases and you see examples of SQL online, you are going to see a variety of how those tables and columns are named and capitalized. In one database, everything seems to be lowercase, perhaps using underscores between words. But in another database, the words are capitalized and smushed together, or even ones where everything is uppercase. It sometimes feels a bit like watching fashion trends come and go over the years. Now, way back in the day, naming was all about being short and sweet because we had a lot of constraints on memory. You wouldn't use 10 characters if you could get away with 3 or 4. So a table wouldn't be called customer, it would be cust. Or a column name wasn't employee identification number, it was EmpID. But as tech got better and we got a bit more room to breathe, the names in the databases could be more descriptive. We went from abbreviations to complete words to multiple words to make it more obvious what is that table for? What does that column represent? And with multiple words for tables and columns, there's various opinions on whether you should use snake case, where everything is lowercase, but you separate multiple words with underscores, camel case, where the first word is lowercase, but any subsequent word is capitalized, like the hump of a camel, or Pascal case, which is similar to camel case, but where you also capitalize the first word. Some styles are more common with particular software vendor or technology. Other times, your organization might have naming practices that they enforce or support. And it can even be down to the personal preference of the database administrator or whoever decided to name those tables and columns in the first place. Now, SQL doesn't care. SQL does not care other than if a column is defined as employee underscore ID in the database, then you're going to write employee underscore ID in your SQL. Now, in addition to capitalization, there is also a lot of debate around whether tables should be named in plural or singular form. So is it a customer table, singular, because each row represents one single customer? Or should it be a customers table, plural, because it holds multiple customer rows? Now, I might get into that debate if this was a course on database design, but as we're focused here on just the pragmatic and practical issues of writing SQL to work with existing databases, let's just be pragmatic. Differences in naming exist. We need to deal with it. Okay, we can hope that within each database we're dealing with, there is some kind of consistency, that we're not dealing with some random collection of. To work with existing databases, let's just be pragmatic. Differences in naming exist. We need to deal with it. Okay, we can hope that within each database we're dealing with, there is some kind of consistency, that we're not dealing with some random collection of some tables are in plural and others are in singular, and some columns are in camel case and others use snake case. That would just make it really annoying to read and write SQL. But you will encounter different styles. So even in the SQL examples I'm going to use here, I will occasionally change from using one style to another because you should expect to see it. When writing SQL, most of what we do can be accomplished using just a few words. But even so, there's one of these words you are going to write more than any other. And it's often the very first word you write in a new line of SQL. And that word is select. It's how we say which columns, which pieces of data we're interested in retrieving from the database. It's how we choose. It's how we make a selection. And it's normally used together with another word of SQL, from. We select specific columns from a specific table. So imagine we have a database with a customer table. Any table might have dozens of different columns, but let's say that the only data I'm interested in right now is the column called email. Then I could write the SQL select email from customer. And that's it. When I run this SQL, the result I get back is just the data in the email column for every single row in the table. So if there were 5 rows in the customer table, I'd get 5 emails back. If there were 5,000 rows in the customer table, I'd get 5,000 emails back. Now, we might call this the results that we get. You'll also hear the term result set because it can be a set of data, a bunch of different results all gathered into one. But we're not restricting these results in any way yet. We're also not organizing or sorting them, so they aren't in any particular order. We'll get to that. If I wanted to retrieve more than one column, I can just write those column names separated with a comma, like select email, comma, postcode from customer, or select email, comma, last name, comma, first name from customer. And if I just wanted to retrieve all of the columns from this table, well, luckily we don't have to write every single column name in full. We can just use the asterisk to represent all columns. If I was reading this aloud, I would typically say select star. So select star from customer. Now you might have noticed I've written a semicolon at the end here. And the semicolon in SQL is like using a period or a full stop at the end of an English sentence. It's how you say this sentence is finished, it is complete. Now, while we talk about the English language as being written in sentences, we talk about SQL as being written in statements. So this is one complete SQL statement here describing the columns to retrieve from a specific table, and this statement is ended or terminated with the semicolon. Some database management systems do not require you to write the semicolon at the end of every statement. It would be understood without it, but it's good practice. It makes it obvious, and I'll be using the semicolon at the end of all my statements. Sidebar. A very common question when someone's first learning SQL is, where do you actually write it? I mean, is there a particular piece of software? Is there one specific application you're supposed to use? And the short answer is no. It's better to realize you have a lot of options. Because SQL is such a standard, there are many different applications, tools, and websites across multiple platforms where you might end up writing SQL. Kind of depends on the situation. The kind of tools you want if you're a software developer are different from the tools you'd want for data analysis and reporting, which are different from the tools you'd want for doing database administration. But okay, you're going to write the SQL somewhere. So let me give you a quick overview of the kinds of tools we often use to write SQL. First, each major database vendor typically provides their own tools that you can install and use. For example, MySQL has MySQL Workbench. Microsoft SQL Server has SQL Server Management Studio. PostgreSQL has pgadmin. Now, these applications are not just a way for you to write some SQL. And when you're new to this, you'd probably find them to be overkill, even overwhelming, because these are fundamentally database administration tools. Yes, we can use them to just write some SQL and browse the database, but they do go way beyond what we're talking about here. They have features for database configuration, database design, user administration, security, permissions, performance, and optimization. But I do want to be clear about something. Even if you're using a particular database management system from one particular vendor, that does not mean you have to install software from that vendor just to write SQL to talk to that database. You don't. Now, in addition to these vendor-specific tools, there are also general-purpose database applications you can install on your own machine, like dbeaver and Razor SQL. Now, these applications are vendor agnostic. They're designed so you can connect to multiple kinds of database management systems. For example, in this dbeaver application here, I have the option to connect to a database, and I'm immediately offered many different kinds of DBMS. I can choose Oracle, MySQL, SQL Server. There are dozens of others. Now, after choosing any of these, I have to provide connection information. Where is that database? Is it on a local machine on my organization's network? Is it running in the cloud somewhere? And how do I authenticate to it? Is it a username and password or something else? But once you're connected, you can then browse that database. You can look at the details of it. You can look at the data. You can write and execute SQL. But as with those vendor-specific tools, these applications are also not just for writing SQL. They're often intended for managing, administering, configuring databases, so they have a lot more features than we need to focus on here. But I don't want to give the impression that you have to install one of these applications at all. You don't. You may not need to install anything because there are more and more web-based applications that allow you to write SQL. So if your organization gives you access to a data processing or analytics platform like Snowflake or Databricks or Tableau, Power BI, and there are plenty of others, you're able to write SQL just within that web application without needing any kind of external editor. With the growth of cloud computing, any databases that are hosted in the cloud, the vendors offer web-based tools to interact with them. So whether it's a database at Amazon or Google or Microsoft Azure, you can often write and run SQL queries directly in the browser without needing to install any software locally. And finally, if you're a software developer, well, you probably just want to use your normal development environment for writing SQL, and you typically can, whether it's Visual Studio or Eclipse or Xcode, you'll typically see automatic color coding for SQL together with options to run and execute that SQL within your IDE. But with all of that said, the majority of what I'm going to do here, I'm not using any specific editor. I'm just going to focus on SQL by itself in a way that could work with any of these applications or environments. When you're writing SQL to select some information from a table, most of the time you don't want absolutely everything, every single row in the table. You only want some of them. So instead of saying, give me the email address of every customer, it might be, give me the email address only for those customers who've made a purchase in the last 30 days. Or I want the contact information of employees, but just the ones who work in the marketing department. Or just the ones who've joined the company in the last 5 years, or just the ones who have a salary between this amount and that amount. And we do this by adding another SQL keyword, where. We don't use where by itself. It's used together with select and from. So I have a table here of movie information with columns like title, studio, director, year of release, genre, length, country, etc., etc. Now, if I write the SQL select title from movie, I will get all titles from all the rows. So if I add the where keyword and it goes after the table name, so first I better make sure to remove the semicolon. We don't want to terminate the statement here anymore. And then add where release year equals 2005. And now I'll use the semicolon. I execute this, I get a smaller amount of data. It's still multiple rows, but only those rows matching this condition. This statement is pretty simple, but this format, this basic structure of an SQL statement with select, from, and where, the columns that you want to select, the table those columns are from, and the conditions where the row should be returned, this is the most fundamental, most indispensable, most essential building block of SQL in any relational database. Yes, we're going to get more advanced. We're going to use multiple tables. We'll write way more complex conditions. We're going to summarize and group and sort our results. But all of that is kind of the icing on the cake on top of this. And in addition to calling this an SQL statement, we could call this a query. Query meaning we are asking a question of the database. This is the Q in SQL. It is structured query language. And getting really comfortable with this, select, from, and where format, this is the tentpole, the cornerstone, the foundation of using SQL. You will never get to a point where you're so advanced with SQL, you don't need select, from, and where anymore. You will use this all the time. So let's try another. Select star from movie where title equals Citizen Kane. Now notice that if I'm dealing with a column that's defined as a numeric value data type, I can just write that number directly. But if I'm dealing with a column that's defined as holding text, it's got a string value, I need to write the value inside quotes. And these are single quotes here to mark the start and the end of that string. Let me say that again. In SQL, you use single quotes to mark the start and the end of a string value. And I stress this point because a lot of other programming languages use double quotes around strings, and a lot of programmers can kind of type double quotes out of habit. Now, some database software can be configured to allow double quotes, but classic regular SQL uses single quotes, and that's what I'll use here. So I'm asking now for only those rows where a column is directly equal to some value. I might also want to retrieve rows that are not equal to some value. And in SQL, not equals is written as the greater than, less than signs, and they're both written together. You don't put a space in between them. So this would now retrieve all rows with a release year other than 2005. And this would retrieve all rows except for the rows of the title Citizen Kane. If we use the greater than or less than to mean not equals, you might wonder, well, can we also use greater than or less than by themselves? And absolutely. I could ask for movies with a release year of greater than 2005 or less than 2005. I can also use greater than or equal to or less than or equal to. But again, if you're using these, the two characters must be written together without a space in between. But this is how we start to filter our data, by making comparisons, by choosing to include or exclude certain rows. And we can build on this to make more complex conditions. Often you want to retrieve rows not just based on a single value in a single column, but looking at multiple columns at the same time. Like, I want the names of employees who joined the company before 2020 and also have a role of manager. Or give me the names of all products that are in the electronics category and also have a price over $100. And sometimes you want an either or situation. Perhaps I want the names of products that are either in the electronics category or have a price over $100. And we do this in SQL using the words and or. Now, these are SQL keywords. I will write them in uppercase to make that apparent here. So for example, select first name, comma, last name, comma, email from the employee table where date hired less than 2020, 1st of January, and position equals manager. Or select product ID, comma, product name from the products table where category equals electronics and price greater than 100. So this where clause, our condition that we're searching on, now has two parts to it. And the terminology you may sometimes hear is that each part is called a predicate. That simply means that each individual piece of this condition can be evaluated as either true or false. And then the entire condition can also be evaluated as either true or false. So this will look at every row in the product table. If the value in the category column is electronics, this piece, this predicate, is true. In addition, every row also has a price column. If the price here is greater than 100, this is true. If it's equal to 100 or below 100, this is false. And because we use the and keyword in between them, we're only going to get the rows returned where both of these things evaluate as true. If I change this and to or, this is now going to return rows where either of these things are true. It's either in the category electronics or it has a price over 100. Now, as you start to build more complex conditions, you're going to start needing parentheses around the different parts of the condition, particularly whenever you have a mixture of ands and ors. The reason you use parentheses in SQL is kind of the same reason why you used parentheses around math problems at school. Now, wait. Even if you hated math problems, trust me, this isn't a hard one. Cast your mind back to if you ever saw something like this. 2 plus 3 times 4, but that there's something called the order of operations. You're not supposed to just go through this left to right always. Some of these operations take priority over others, and multiplication is supposed to happen before addition. So by default, as this is written, you're first supposed to multiply 3 times 4 to get 12, and then add 2 to end up with a final result of 14. But you can add parentheses to refine these and specify your own intended order. And now the parentheses tell this operation we're supposed to do this part first. So now we're supposed to add 2 plus 3 to get 5 and then multiply by 4 to end up with a different final result of 20. How does this apply to SQL? Well, let's say I've got a products table and I want to retrieve all the products in the electronics category as well as products in the books category that have a price less than $10. Now, I might begin with SQL like this, where category equals electronics or category equals books and price less than 10. Now, this looks okay. And here's the thing. This SQL will work. There's nothing invalid about the syntax. It won't cause an error and I will get results. I'm just not going to get the results I wanted to get. That's because we also have an order of operations in SQL. Just as multiplication is regarded as more important than addition in a math problem, here, and is regarded as more important than or, and it gets evaluated first. We fix this with parentheses. As with a basic math problem, we're now saying evaluate this part by itself. So it now finds any rows where the category is books and the price is less than 10, in addition to any rows where the category is electronics. And when you first start to write more complex conditions in SQL, it's not a bad idea to go a little bit overboard with the parentheses to make sure your conditions are being evaluated in the order that you want them to be. Often you need conditions where you're looking for rows that don't just have one acceptable value, but several acceptable values. Let's say I wanted to find employees that are either in the sales or the marketing or the engineering department. Now, I can certainly do this using the or keyword like this. But if we also then needed to include accounting and then HR and then IT, this starts to become very cumbersome and it's harder to read and maintain, particularly if you then started adding additional columns to look at in this where clause. We can simplify this using the in keyword. In lets us use the column name once and then search for multiple values in a single swoop. So we use one set of parentheses here, and then each acceptable value separated by commas. Now, department is defined in this table as a text column, so each value here is in single quotes. So by using in, we just make this query a little bit cleaner, a little bit more concise. And now if I wanted to add additional departments, I don't need another or department equals lines. I just add the new name to the list. Now, I might sometimes want to exclude a range of values, like finding employees who are not in certain departments. And I can do this by just adding the word not, where department not in sales, marketing, engineering, etc. We can also use the in and not in with other data types like numeric values. But what's often more common with numbers is you want to describe a range, more than this and less than that. And okay, we could do that with the options we've already seen. We could select star from artifacts where year is greater than or equal to 1900 and year less than or equal to 1950. But alternatively, I can use the SQL keyword between and just put where year between 1900 and 1950. And between is inclusive. This will bring back any rows that have the value 1900 all the way up to and including 1950. In a simple example like this, changing to between might not seem like it saves very much, but when you're writing more complex conditions, it can really help clean things up. It reduces the amount of parentheses you need. It reduces the amount of times you need to write the column name. For example, if I had a condition that looked at two different columns for ranges of values, I could certainly do this without using between, but we'd need to use parentheses to separate the different parts of this condition. Now, let me just kind of quickly read this aloud to make the point. Select star from artifacts where open parentheses year greater than or equal to 1900 and year less than or equal to 1950 close parentheses and open parentheses weight greater than or equal to 100 and weight less than or equal to 500 close parentheses. But it's much easier to just say select star from artifacts where year between 1900 and 1950 and weight between 100 and 500. Simpler, more straightforward, more concise, easier to read, easier to say. Now you can also use between with dates and times, which can be very useful to describe date ranges, like selecting all orders for a particular month. And most DBMSs allow us to deal with dates kind of like the string values. You use the format of year, month, day, and they will understand what's meant by that. But there are often multiple ways that you can write the same condition. Some of this comes down to personal preference of what you think is more readable, more obvious, but focusing on the more concise options is always a good idea. Sidebar. Some computer languages are case sensitive. If I have some valid code written in Java or C# or Ruby or Swift, and I just started randomly changing a bunch of these letters from lowercase to uppercase or vice versa, this code is going to stop working. Those languages are case sensitive. Now, SQL looks like it's case sensitive. When you read it, you typically see a variety of words in uppercase and lowercase. It looks like this is very important, but it isn't. SQL is not case sensitive. SQL is not case sensitive. I could have written this statement with the word select in all uppercase or all lowercase or even a bizarre mixture of the two. It would have worked just fine. The reason it's often written like this is for readability. It just makes it easier to quickly scan and recognize the different parts of an SQL statement. And it's quite common to see SQL keywords written in uppercase. When I say keywords, I mean those words that are defined as having a specific meaning in the SQL language. So in a statement like this, these are SQL keywords. They are part of SQL. They've been part of SQL since the 1970s. But the column names and table names that I'm using, those were defined in, well, whatever database I'm using. They were chosen by whoever built that database. And you're going to find that variety of naming conventions depending on when the database was made, who made it, what naming styles were fashionable at the time. So even though it's not required, I'm going to write my SQL keywords all uppercase, and things like column names and table names, I'll just write them however they were defined in that database. However, there is one aspect of this worth talking about, one place where you might actually care about case sensitivity, and that's when you're searching on a specific piece of text. Let's say I'm looking for a movie with the title Citizen Kane. I might want this query to work regardless of how that title is actually capitalized when it was stored in the database, whether it was all uppercase or all lowercase or capitalized. Now, but sometimes I might even want a case-sensitive search where it would only match against rows with that exact capitalization. Now, you can do this. It's one of the places where different database management systems handle it in different ways. Now, most databases, this can be configured so text searches are either case-sensitive or case-insensitive by default. It's something called the collation settings. And with some database software, collation is configured at the database level, so it affects the entire database. With others, you can configure this collation option at the table level, even the individual column level. You could have one column in a table that's case sensitive when you're matching against values, and another one that's case insensitive where it just doesn't care. Now, we're not going to get into the database configuration specifics here. Just understand that SQL itself is not case sensitive. But if you want to get specific about doing case-sensitive or case-insensitive searches within the SQL queries, then look at the documentation for the specific database software you're using. And another sidebar, you see, all computer languages also have this idea of white space, the characters you can type in your code, but you don't actually see on the screen, like spaces, tabs, and line breaks. Now, some languages, like Python, treat white space as important or significant. Python uses indentation to determine the structure of your code. So if you change the indentation, it affects how that Python code works. But other languages, like SQL, regard white space as insignificant, which basically just means SQL doesn't care about how many spaces or tabs or line breaks you put between different parts of an SQL statement. It doesn't affect how the SQL works. It's just for readability. So I could have written this SQL statement on one line or two or three or more. I could use tabs and spaces and line breaks. It all works the same way. Okay, you're not allowed to use white space within a keyword. So you can't split the select keyword across two lines. And yes, you also need at least one space between the different parts of a statement. But other than that, white space is just for improving readability. Again, the only exception to this is when you're working with a specific value of text that you'd naturally want to be white space aware. So if I was searching for the value green tea as written here, well, then this space is significant. It's going to match against values in the database that are equal to green space tea, not green tea if it was written as one word or green space 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 tea. So yes, white space does have meaning within string values, within the quotes, but in the rest of your SQL, it's just for readability. And that's why in this course, I often split the statements onto multiple lines just to make it easier to talk about. End sidebar. Now, we often want to match on an exact value. So here, only returning a product where the name is equal to green tea. But if you need to be a bit more flexible when matching text, you can use the keyword like, and ask if a column is like some value rather than equal to some value. I'm going to add a percent sign here, and this is written inside the quotes. I put it after the word green. And in SQL, the percent sign acts as a wild card. We're now going to find products where the name begins with green, but could be anything after that. So this would match green tea, also match on green coffee beans, green yoga mat, and so on. However, this will not match a product with the name jasmine green tea because the word green is not at the beginning. If I wanted to find any products that had the word green anywhere in that column value, I could add another percent sign before. And the percent sign is a very flexible wildcard. It will match on any amount of text or none. So having the percent sign at the start doesn't require there to be any text before the word green. It's okay if there isn't. So we'll now match on products that have the word green in the middle or at the start or right at the end. Now, sometimes you don't want that much flexibility. You might just want to support a single character wildcard, a single character that could be different. You can do that with the underscore, still using the keyword like. So this SQL is going to look for rows with the value Genesis G, some character 0 in the name. So this would match on Genesis G70, Genesis G80, Genesis G90, but this would not return on GV70 or GV80 because it's only going to match if there's a single character between the G and the 0. Now, you can also use like to exclude certain results, and we could just change like to not like. So where name not like green, we'll find every product where the name does not include this word. But one last thing I'll say about using like is even though it is sometimes necessary, it can be inefficient and time-consuming because it is demanding on the database to search through the values in a column. Now, this can depend on the size of your database and how the columns have been defined in the table, but even so, the same wildcard can be significantly more or less efficient depending on where you put it. Here's what I mean. So I'm going to search the stock table here for any rows where the inventory code begins with the letters ABC. The wildcard is at the end. Now, if I execute this SQL and the DBMS only needs to look at the first few characters of that column in order to either include it or rule it out. But if I simply added another wildcard at the beginning, so the letters ABC could be anywhere, it's a trivial change to this SQL, but it's much more demanding on the database because the DBMS cannot just look at the first few characters anymore. It has to search for this pattern anywhere in the column, which is much more inefficient. This is not a course where I'm going to get into performance and optimization of SQL queries. That's an entirely different course by itself. But what I want to point out is just because something is simple to write in SQL, like a wildcard search, that doesn't mean it's also easy for the database to do. And a task like asking the database to search through an entire table for a piece of text that could be anywhere, that is one of the most inefficient things you can ask a database to do. It's just that sometimes you need to. Some columns can be configured to allow null, and null meaning the lack of a value, the total absence of a value. Now, making the decision about whether a column does or does not allow null is typically up to the database designer or database administrator. But when we're writing SQL, we often need to work with columns that might be null. So here I have a table including columns for first name, last name, and middle initial, but where this column is configured to allow null if people don't have a middle initial. If they don't have one, this value isn't space, it isn't empty string, there's no 0, there's simply no value here. So if I wanted to ask for those rows where the middle initial has no value, where it's null, I might first try writing SQL like this. Select star from employee where middle initial equals null. But this won't work because equality is not the right idea when you're dealing with null. Something can't be equal to null or not equal to null because null is not a value. And in SQL, we use the word is when we're working with null. So we can ask where middle initial is null, not equals null, just where middle initial is null. Conversely, if I wanted just those that have some value in that column, we could say where middle initial is not null, meaning it's got some kind of value, and then we could execute that code. Now we only have the rows where that column has a value.